things around for us here. Okay. Well, exponentials can do growth or decay. Now, first of all, let's just assume that A is something positive for right now. Okay, we'll switch that around later. So, A is positive, A is positive. If that A is a positive number, and I want my exponential to be a growth, what has to be true about the base? It has to be not just positive, more than positive. Yeah. Larger than 1. Think about that. The base is the number we're raising to the exponent. If that number is something less than 1 and I raise it to a really large exponent, what's going to happen to the value of it? It's going to go down, right? If you repeatedly multiply a number that's less than 1, it's going to get smaller and smaller and smaller and smaller. It's going to create a decay. But if that number is bigger than 1, then you're multiplying by something again and again and again that's going to cause this thing to grow as you do it. So to make a growth, again, as long as A is greater than 0, B has to be greater than 1. And a decay, like we just said, B has to be less than 1. But it can't be any smaller than what? 0. If it's less than 0, it's actually not even exponential anymore. So it works kind of like that. If it's a growth, if the A is greater than 0 and the B is greater than 1, yep, kind of like the last one we just looked at. If A is greater than 0, then the B is between 0 and 1. That's going to create a decay. All right. So, yeah, this is all the A greater than 0 stuff. Now, what if I switch that around, though? So what if A is a negative? Well, then it's exactly the opposite. If the base is between 0 and 1, it's actually going to grow. And if the decay, or if the base is greater than 1, it's going to decay. All right, and I'll show you a quick sketch of what each of these different situations looks like, so you can kind of see what's going on. And there's some connections between them, too. Okay, so this first one, where you have your base is greater than 1, A is positive, that's going to create a graph just like the one we looked at with that example we did. It's going to do something like this. If that base is between 0 and 1, but A is still positive, then it's going to do something kind of like this. Okay, so growth, decay, right? Now, if I let A be something negative, think about this for a second. This actually relates to something we've talked about before with transformations. If I stick a negative in front of a function, which is essentially what I'm doing when I make A negative, right? What happens to the graph of a function if I suddenly just make A negative? It doesn't move it down. It reflects it down, right? It reflects it over the x-axis. Okay, so this one right here, do you see how this growth and this decay are pretty much the same thing, except now A is negative compared to being positive? So this graph here, this one we're about to do, is the exact same thing as this one, just reflected down over the x-axis. So it looks like this. Okay, so do you see how a reflection of this second one down to here turns a decay into a growth? Right, because it's actually increasing as it goes. Okay, so this is actually a growth. That's why that opposite thing works, where the decay kind of becomes a growth and the growth becomes a decay. So this last one, then, it's the same kind of story with the first one, then. It's a reflection of that first graph over the x-axis. And so it looks like this. Has that kind of a shape to it. All right, and each of these has A as your y-intercept, because it's that initial value, right? We said when x is equal to 0, that's where A is. Take a look at the first two. For the first two, isn't A positive, right? We said for both of these, this is when A is going to be bigger than 0, so those are both positive. Over here, we said A is going to be less than 0, so those are both negative. Okay? So again, that initial value, it's when x is 0, it's a y-intercept. On the graph, you can kind of determine where those are at that way too. Okay? So, now the question becomes, can you sketch a graph of one of these for me then? So if I give you an exponential equation, can you determine which one of these four categories it falls into and sketch what that graph should be? So we'll try a couple of those and then we'll move on, but let's see if we can do that. All right, so let's try this one. So sketch the graph and then indicate, is it a growth or a decay? Because part of your homework, they're going to ask you just indicate if this is a growth or decay. So if you can graph the thing, then you can look at it and just answer the question then. All right, so -2, 1/2 to the x. So which of these four categories does it fall into? Is it 1, 2, 3, or 4? So A is negative, right? And B is between 0 and 1, so it's the third one. So it should be a growth. We should be getting a growth here. Okay, so it's going to look like this. Okay, and this y-intercept should be what? -2. Yeah, we know exactly what the number is this time, right? Based on the equation. So that should be at -2. So something kind of like that, all right? It's increasing as you go across it, so this is a growth, just like up here says it should be. Got it. Okay. Let's do another one. So what did I do to this one? Added a constant on the end, this +1. So what's that going to do to my graph then? It would be what? It moves the y-intercept, which direction, up or down? Up 1. Okay. So what I would do is start with just sketching the thing before you do the +1 on the end of it. Okay, well, you know it should look like. And then you can just scoot the whole thing up 1 unit, and you got it. All right, so which category have we got here? 1, 2, 3, or 4? It's the second one, right? It's got A is positive this time. B is between 0 and 1. So this is a decay. And so initially, it would look something kind of like this. Okay? And that y-intercept, before it's been shifted up, would be what? 3. But what is it actually going to be now? Moved up. Should be at 4. So it's going to look like something closer to this, where that y-intercept's actually now up at 4. Okay, so you're going to be asked in your homework to do some matching of some graphs and that sort of thing, and it's going to have some translations thrown in there too, okay, but don't let that throw you off. It's just taking these 4 shapes and then just shifting it up, down, however much, if they happen to add something on the end of it there. And yeah, that's it. Okay, so I actually want to do one more of these just to show you something else you might come across. That's actually still exponential as well. And this is one you're probably going to want to rewrite in a different way to be able to match it up with what you have. Okay? What do I do with that negative x? How could I take that and like change my base to something else? Yeah.
Can't you like make it a fraction and put the x in the bottom?
Exactly. Well, you don't put the x in the bottom though. I guess you could, but we don't want to. So in any event, I like the fraction though. So 1/2. If I was going to strip the negative off of that x, this would be 3 to the negative 1, right? Kind of doing that power of a power trick like we talked about before with the fraction, okay? But what is 3 to the negative 1? No. It's 1/3, right? It's not negative 3, it's 1/3. So what we actually have here is 1/2 times 1/3 to the x. Okay. So to sketch that then, we have a is greater than 0. Our base is between 0 and 1. So this is going to be second category again, right? B is a fraction. So it's going to look like this. And what should be that y-intercept? 1/2. Okay, so I just wanted to show you that because I remember last year I didn't do this example and there was a negative x, actually there's several of them in there, and that threw some students off. But that's all they're talking about though. Okay, it's actually exponential still. Negative x is just another way of writing a fractional base in that way. Okay, so exponential I wanted to look at with you guys. Let's quickly talk logistic and then we'll be done. All right, make sure that's still on there. Okay. All right, so a logistic function. 2 different ways they could be written depending on how you're going to do it with what base. We'll probably stick with this one for the most part. So it's c over 1 plus a times b to the x. Now logistics and exponentials are kind of closely related. Do you see the exponential function that's been kind of just stuck in there? That little a times b to the x is part of that. The c is called the limit to growth. Okay, here's the difference. With exponentials, and this is just assuming like the basic exponential, everything's positive, b is greater than 1, yada yada. Exponentials do this, and they just keep going up, right? Doesn't do that. It grows like an exponential, but then it levels off eventually. It does something like this. So it heads up, and then it says, nope, I'm not going to keep going. Going to level off like that. So it starts to look exponential, but then it stops. Okay? And logistic functions are useful because when we get into modeling tomorrow with functions, the way like populations work, most people assume that populations are always exponential. Have you heard that before? That populations always grow exponentially. They just keep getting bigger and bigger and bigger and bigger and just keep going off. Technically, that's not true. We have a finite